So yesterday we talked about Faraday's law, and we ignored part of it. Faraday's law is induced EMF is negative derivative of the magnetic flux. So if you have a changing magnetic flux, you're going to induce an EMF. But there's this negative sign. That tells you about direction. We figure out the direction, though not from Faraday's law, because it gets kind of complicated unless you have a function. You figure it out from Lenz's law. So Lenz's law says when the magnetic flux changes through a coil, the coil will have current flow to produce its own magnetic field that opposes the change. So when you change the magnetic flux, the EMF produces a current that makes a magnetic field that is in the opposite direction of that change. Now it's opposite of the change. It's not opposite of the field. It's opposite the change. And we're going to do a series of examples. But before we do that, I want to remind you of the source right-hand rule. So in the source right-hand rule, your thumb pointed in the direction of the current and your fingers curled in the direction the magnetic field it made. So did like this. So if we had current flowing in a wire out of the page, then we'd point our thumb out of the page and we see the magnetic field it makes goes counterclockwise. So we draw a B field counterclockwise, and it would do concentric circles and they'd be all up and down here. But that's how we figured out the direction of the magnetic field it produced. Well, what if we had a coil of wire, like we're talking about here? So we have a coil of wire, and let's say the current in that wire is clockwise. So now to do this, I can't just point my thumb one direction because I have current flowing in lots of different places. So if I lay my finger on this side of the loop, so it's pointing towards the top of the page, my circles go around and around and around, and specifically they go into the page on this side and out of the page on this side. So right on the outside of the loop I have into the page, so X's, and just inside the page I have dots, because into the page, out of the page, into the page, out of the page. If I move my thumb to the top, into the page above my thumb, out of the page below my thumb. So right close to the wire, into the page, out of the page. And I continue around on the left side, into the page there, out of the page here, into, out of. And you can guess, point our thumb at the bottom, out of the page above the wire, into the page below the wire. So here's a nice thing. This rule is reversible, and it makes it a whole lot easier to figure this situation out. So if you reverse this, so your finger is curled in the direction of the current, your thumb points in the magnetic field direction, in the middle. So to show this, curl your fingers in I, and notice B points out of the page, just like we already figured out from the original version. So when it reverses, your fingers curl in the I direction, thumb points B in the middle of the loop. So now that we have this, that if I have a loop of current, I know the magnetic field in the middle is in the direction of my thumb. We're going to use this with Lenz's law to figure out, so how does current flow in a bunch of different situations. So I have a series of examples for you, and I don't want to draw small. So let's make sure we're near the top of the page. So we are going to start with a loop of metal in a magnetic field that points out of the page. So something's making this magnetic field. We don't know, we don't care. We just know there's a plain loop of wire, no battery, no switch, no anything, just a loop of wire in this magnetic field. So in situation A, we're going to turn off the magnetic field B. I should probably label those. So here's the coil. We've turned off the magnetic field. Lenz's law says that this loop of wire is going to make current flow in order to boost a magnetic field that opposes the change. This is a lot like a toddler. Toddlers do not like change. If a little kid is playing with blocks and you say, it's time to go to grandma's house, you know how much you'd like to go to grandma's house. No, I don't want to go to grandma's house. I want to keep playing with my blocks. Well, you finally get the kid up, throw him in the car, you go to grandma's house, have a grand time as you knew you would. And then it's time to go home. I don't want to leave grandma's house. I don't want to go home. But you want to go back to what you're doing before? No, now I'm at grandma's house. I want to keep doing that. Well, you finally get the kid home and you're reading books because it's time to go to bed. And you're having fun reading the books as you knew you would. And then, oh, it's time to go to bed. No, I don't want to go to bed. I want to keep reading books. So it doesn't matter what the particular activity is. Toddlers do not like transitions. They need good warning. In fact, my child's still like that. You know, a lot of people are like that. We don't like transitions, especially without warning. So this loop doesn't want this to happen. It wants to keep this magnetic field. So it's going to make its own. So if this magnetic field is out of the page from some external source, this is going to make a magnetic field out of the page. To do that, my thumb, magnetic field out of the page, current must flow counterclockwise. So again, we are opposing the change. Magnetic field out of the page, no magnetic field. This wants to keep what it already had, this magnetic field. So you point the magnetic field out of the page and your fingers curl counterclockwise. So we're going to start with the same situation. B out. But in part B, make B stronger. So same loop, lots and lots and lots, way more dots than before. Much stronger magnetic field. But again, we're opposing change. So the loop does not want more field. It wants to keep this amount of field. So if you give it more, it's going to say, I don't want more. So it's got to cancel it out. It cancels it out by making one in the opposite direction. So for it to make a magnetic field into the page, to cancel out this increase, current has to flow clockwise. So compare and contrast the two cases. We got rid of the field, it wants to keep what it already has, you point your thumb out, fingers curl counterclockwise. We make more, it doesn't want more, so it makes it cancel out an inward field, current is clockwise. So now C, we're doing a total of 5 by the way. So there's the original magnetic field. We are going to reverse the field. So I need to draw X's. The loop doesn't want to reverse the field. So it's going to say, I don't want this thinking inward field. I want to keep the outward field point. So it makes a field outward, which requires counterclockwise current flow. Notice that's just like A, because to reverse the field, you first have to turn it off. So you turn it off and you keep going, and it says, no, I want that original thing. So it does same direction. Now in D, same way to start. We are going to pull the loop out of the field. So the field's still here, but the loop is over here. So we pulled it out physically. We've grabbed the side of it. Well, if we do that, the loop says, no, I want a magnetic field in this direction. So it's going to make that one that direction. And so counterclockwise current flow. I can't do my arrows. And then we're going to put it back in the field. Put it back in. So I'm going to recopy what I have here. And then the after is it's back in the field. But when you put it back in, it's forgotten about this situation. It's remembering this. So now it says, I don't want a magnetic field. So if you're going to make me have a magnetic field outward, I'm going to make an inward one. And we get clockwise current flow. Notice how these two are opposite to each other. When you pull it out, it says, I want to keep that out. When you pull it, remove it from the field, let's use that wording. When you remove it from the field, it wants to keep an outward pointing field, magnetic field, and so it makes one, and it's counterclockwise current flow. But then when you put it back in, it rejects the new, and it makes a canceling field inward to the page, and current flows the other way. So if you do this at a steady rate, say you had a mechanical arm that pulls it out, pushes it in, pulls it out, pushes it in, you're going to get the exact same amount of current, but in opposite directions. And so you would get a negative and a positive and a negative and positive. And this is that alternating current flow that we were talking about yesterday. So there's one more interesting consequence of this, and it's called an eddy current. So an eddy current, eddy in general means something that's pretty transitory. It's small. You'll talk about eddies in water, that they're little tiny like whirlpools and things out when a boat passes, but they don't last for very long. So these are currents that don't last for very long. And the most common of this would be in a long metal tube. And we're going to drop a magnet inside of it. So let's say this magnet is dropped north down, so the magnetic field is this way. And if we imagine just this one little section of the tube, this is a coil. So a current is induced because the magnetic field's getting stronger as it gets close here, and then it's going to be, and then it continues downward, so it gets weaker again. But also we have a direction issue. So this is making a magnetic field towards the bottom of the tube. That loop says, I don't want a magnetic field, so it makes a loop toward a magnetic field towards the top of the tube. And you would see a little tiny bit of current flow this direction, like viewed from above, that's counterclockwise. But one thing I want to point out is because it's making a magnetic field the opposite direction, that field is going to be detected by this magnet as a force back on it. I hope that sounds to you like Newton's third law, because that's what's happening here. That's how this magnet is interacting with any metal tube, not just a magnetizable object. It sets up a current, and then it is opposed by that field produced by that current. Even after the magnet goes through, now this loop says, hey, wait a minute, you made a downward pointing field in me, and now you're going away. I want a downward field. So now it's going to make a field downward. And so you would see this very small in time current go the opposite way. But if it's making a down, now it's on the south side where the field is pointing that way, it's going to attract it and pull it back up. So one of the ways to explain eddy currents, or even Lenz's law, is the universe doesn't want to gain energy. It can't gain energy. We have a law of conservation of energy. So if you have a change, there's an opposing change to cancel that out. At least they try for the whole system. We will do this in class, and it's kind of fun. There are some other interesting circumstances of it. The other thing I'm going to have you do in class, not only practice Lenz's law with the source right-hand rule and which way is current going to flow, but I'm also going to have you go back to a couple of problems now and use Faraday's law, so that now you can figure out when there is an induced current or an induced EMF, what direction does current flow, as well as how much current flows.